we are going to pick up back where we left off for Sensation and Perception, Chapter 9, where we're talking about color constancy. We were talking about color deficiency right before this, and this is just sort of ending out the chapter with the last few slides. So there's a YouTube video on the bottom here where it's a really neat video where they cover the dress, and is it blue and gold, is it white? And that's a really neat kind of explanation using color constancy to explain why the perception of the dress is sometimes one color or set of colors versus other colors. And it really has to do with the environment in which the dress is being viewed in. And so we're going to talk about a couple of other things like this when we get into hearing that are similar in concept. But color constancy is when we perceive colors to be pretty constant, regardless of what light source we're viewing it in. Actual light reflected from, let's say, a green sweater depends on two major things. One is its reflectance curve, which we're going to get to in this slide right here. And the other is the illumination that reaches that item and the light that's reflected from it. So when we look at different kinds of light, for example, in right here to the very left, you can see, and this is an example using a red sweater or a green sweater, I believe. Yes, a green sweater. Looking at different kinds of light reflecting, we have sunlight, we have incandescent, tungsten filament light, and LED light. When we look at the different kinds of light, we see that sunlight does have approximately equal amounts of energy, and so that tends to be kind of the most reliable source of reflectance. And then tungsten lighting, which is more like the kind of old-fashioned light bulbs where it has kind of a yellowish appearance, that has more energy in the long wavelengths, which is why we see everything having a sort of a yellow tinge to it. And then LED lights, they emit at shorter wavelengths. They emit light at shorter wavelengths, which is why they have kind of a blue reflectance there. And of course, we see that objects reflect different wavelengths from different sources, whether it's sunlight, whether it's tungsten lighting, whether it's LED lighting. And that is, these different light sources can impact sort of the shade of the color. But in the case of, for example, a green sweater, it should still appear to be green in all of those instances. Well, whereas in the sunlight, it might be a slightly lighter shade of green, and in indoors in different tungsten or LED lighting, it might be slightly darker. But color constancy is this idea that colors really do remain relatively constant despite changing that light source. And now chromatic adaptation is also an explanation for why we see in certain cases the color may be the same, it may hold constant, but it might degrade a bit in saturation. And so we call this chromatic adaptation when we are exposed to a chromatic color, so anything other than, white, black, and gray, when we adapt to this color because our cone pigment bleaches. And when it does so, then your cones aren't as sensitive to the color. And so let's say you're looking at a red light. When that adaptation occurs, you'll see, or the red color, you'll see the red as less saturated and less bright when that occurs. And so when we see, for example, I'm going to give you an example of an environment where you can kind of look. This would be an example of a lush environment versus an arid environment. And in this case, in this situation, here you're seeing a lot of greens. Here you're seeing more yellows. And the adaptation that occurs is going to tone down these colors. And this is why you see that there are particular more dominant colors given different seasons, is because we adapt to those particular hues, and then that's going to change how we're able to view or perceive the color that's that might be jumping out at us. Now, when we consider, let's see, go back here, and we talked about this idea of of reflectance, and when we consider how important the surroundings are, we know that our visual system uses information provided by the way that objects in a scene are illuminated, and we use this to estimate those characteristics of illumination, and we also make adjustments based on that. And so when an object is surrounded by many colors and in a very colorful environment, then we can see a particular color remaining constant more often. When we have, for example, an object that we are familiar with, let's say a red stop sign or yellow banana, we have representations of what these objects should look like. You know, we know a stop sign should be red, we know a banana should be yellow. Not only does it help us identify those particular items better, more quickly, because our expectation is that it should match with the color, but it also will impact our own perception of the colors. And regardless of what the wavelengths are actually shown, what experiments have shown time and time again is that we perceive the colors of known objects much more richly and more saturated compared to other objects that are perhaps not in our knowledge base. And of course, we use top-down processing in cases where we're looking at a particular object and saying, I know the color of a banana is yellow, I expect that banana to be yellow. And when you look at an object that is the same shade of yellow, that is not a banana, we're much more often going to say that the banana is more saturated and richer and brighter in color compared to the exact same wavelength of yellow. So we definitely are impacted by our knowledge of colors. Now, unlike chromatic colors, achromatic colors, what's important here is not the amount of light reflected by the object, but it's actually the percentage of light. And so again, achromatic colors are also perceived as remaining relatively constant. And one way that we can talk about this is the ratio principle. So the ratio principle is when we see that two areas that reflect different amounts of light might look the same as long as the ratios of their intensities are the same. But this only works on like flat, even objects that are evenly illuminated. For example, a checkered board. So here this ratio, in the case of a light bulb giving out 100 units, is 9 to 90, which is 0.10. And then when we look at, for example, sunlight, which might be 10,000 units, we see this 900 to 9,000 ratio, which still equals 0.10. So regardless of the intensity, the ratio remains the same of 0.10, regardless of the light source. And so this works really well for those flat, even scenes, even illumination, but it doesn't work that well for 3D scenes or where we tend to get uneven illumination. So this idea of constancy and the ratio principle does not necessarily apply when we have 3D scenes. So what happens when we have uneven illumination? So we have to be able to distinguish between edges, and our visual system is actually pretty good at being able to determine reflectant edges versus illumination edges. So reflectance edges, these are when the amount of light reflected changes between two surfaces. And I'm going to give you an example here. So a reflectance edge would be looking at, for example, a difference between A and C. And if you notice A right here, okay, this is a reflectance edge. A is a different kind of brick. It's a different material compared to C. And so you can actually see a difference in reflectance here. And this edge that's created is because these two different surfaces are made of different materials, and these two different materials are going to reflect light differently. So that's a reflectance edge. And then we can have illumination edge, which is where the lighting of the two different surfaces changes. And in the case of this example, we're looking at A to B. And so we're seeing this edge right here, right? And that edge is an illumination edge because A is receiving more light than B. So it's actually, B is actually in a shadow. And so even though we see here that this is the same material, this is considered an illumination edge because the two surfaces change in terms of shadows, but the material of which the type of material is the same. And so our ability to understand the kinds of illumination, the kinds of edges tells us, is this a different object? Is this an edge of an object? Is this a shadow? What's going on? And so shadows are extremely helpful in determining, for example, if it's an illumination edge. So your visual system will take into account the meaningfulness in saying, is this a reflectance edge? If is this an illumination edge? And our abilities to do so rely on experience. So, for example, the meaningfulness of objects. In the case of this palm tree here, we know the shape of the palm tree and we see the shape of the darker part of the brick. And instead of saying, oh, this must be darker brick here, our experience with shadows say, well, that looks like that, and so that looks like a shadow to me. There's also a few other things. So the shape of the tree, the fact that it's a shadow, the different color bricks all tell us, and our experience with shadows all tell us that that is a shadow and not another object and not a change in color in the bricks. There's also something called the penumbra, which is the fuzzy border that's at the edge of a shadow, and that can signal an illumination edge. So I'm going to give you guys an example here. The part right here, this little fuzzy part that's sticking out, that is the penumbrum. And if you alter that in any way, it's actually going to change your perception of the shadow. So you can actually try this at home where you take a cup and you put it on a sheet of paper, and then you can draw with black marker the penumbra here, and notice that it changes your perception of that particular shadow. Our visual system needs this fuzzy part, this system here, needs to be able to detect that in order to realize that this is indeed a shadow. Now, the final thing that I want to cover in this chapter is this idea that everything that we experience, all of our perceptual experiences, are really shaped and created by our nervous system. We know that light waves are not colored. Physical energy in the environment doesn't have these perceptual qualities that we are experiencing. It's the light waves are hitting our retina, hitting our cones, and being able to, and our cones and our visual system is able to take that information and translate it into something that our brains can understand in order for us to be able to perceive color. But the light waves are not colored themselves. It's just how our brains are able to decipher that information. Different nervous systems, of course, experience different perceptions. In the case of a honeybee, honeybees can perceive colors that are outside our human perception. But there's no way of really knowing what a honeybee actually sees. So if we look at this sort of spectrum here, we're looking at how a honeybee is able to see this absorption spectra, because that's what this is. This is an absorption spectra of a honeybee. What is this? What is this wavelength that they're able to see that we can't see? When we see, like, for example, 350 nanometers, what does the bee see? What does the bee perceive at this point? We cannot see this short wavelength. We can't see 350 nanometers. So how is it that, we are seeing this. How is it that the honeybee is seeing this? What are they perceiving? There's no way for us to be able to know, because of course, wavelengths at 350 nanometers don't have a particular color. How is it that the honeybee is able to actually perceive something that is out of our scope? So when we consider all of our perceptual experiences, and we're going to get to, hearing with the ear, we're going to get through all sorts of different other kinds of chemical senses, bitterness, sweetness. How is it that we're able to determine what those things are? And it really comes down to the fact that our nervous system is shaping our experience as well as creating the things that we experience. So if you have any questions, of course, let me know. Send me an email, and I'll be happy to answer those. And this will apply to the exam, the last part of, I believe, exam 3. So if you have any questions, let me know. Have a great day.